Welcome back. Climate change is a long-term shift in temperature and weather conditions. These changes might have natural causes such as through variations in the solar cycle, but these changes also may be driven by human activities. The learning objectives in the upcoming 2 video lectures is to understand the physical principles behind global warming and climate change. What is the role of greenhouse gas emissions and what is the impact on climate change with reference to the different scenarios for CO2 emissions in the future? After these 2 video lectures, I hope you will understand the need for an energy transition towards an energy infrastructure that is carbon neutral or even carbon negative. Let's take as an example the energy infrastructure of the European Union again. Along the energy value chain, whether it's during the winning of primary energy sources like coal, gas and oil, or whether it's during the conversion of the primary energy sources into secondary energy sources, to whether it's during the end consumption in sectors, there are many processing steps in the energy system that emit the greenhouse gas carbon dioxide. The chemical formula of carbon dioxide is CO2. CO2 is formed by the consumption burning of the fossil fuels. On global level, in the year 2023, humankind have emitted 37.4 gigatons of energy-related CO2 into the atmosphere. Let's personalize that. This is 4.7 tons of CO2 per person on the planet Earth per year. If we assume that the average general body weight of a person in the world is 62 kilograms, this implies that everybody on planet Earth has an annual CO2 footprint of 76 times his/her of their body weight. And this is equal to 13 kilograms of CO2 per person per day. If you compare that to the amount of waste we produced, on global level, a person produces 0.74 kilogram of waste per day. The amount of CO2 mass per person we dump into the atmosphere is 80 times more than our daily waste production. You might not realize this, and the reason is simply we don't see directly. CO2 is a colorless and odorless gas. You don't notice it in reference to your waste in the form of materials or substances. What is the impact of our CO2 emissions on the ecosystem of planet Earth? Let me introduce you to the carbon cycles at planet Earth. First, Earth has a natural carbon cycle. In its natural carbon cycle, vegetation on land annually absorbs 440 gigatons of CO2 out of the atmosphere and emits again 4,400 gigatons CO2 into the atmosphere. Similarly, the oceans, including its flora and fauna, absorb 330 gigatons of CO2 and emit 330 gigatons of CO2 per year. Humans emit additionally around 40 gigatons fuels into the atmosphere by burning fossil and land use like deforestation in the tropics. This additionally emitted carbon dioxide is partly absorbed by the biosphere and oceans that results in the acidification of the oceans. Some of the additional CO2 dissolves in the ocean reacts with water to form carbonic acid. Some of this carbonic acid molecules dissociate into a bicarbonate ion and a hydrogen ion. However, a significant part of the by human activity extra emitted CO2 remains in the atmosphere and contributes to the growing CO2 concentration in the atmosphere. The blanket of greenhouse gases is getting thicker. In this plot, you can see how the atmospheric CO2 concentration in the atmosphere has been increasing over the last 175 years. The vertical axis on the right represents atmospheric concentration and is expressed in particles per million. The CO2 concentration has been increased from 280 particles per million in the early 19th century up to 427 particles per million in 2025. Now I have added the yearly global surface temperature anomalies with respect to the average global surface temperature for the period of 1901 to 2000, represented by the horizontal black zero line. The unit of the vertical axis on the left is expressed in degrees Celsius. The blue bars indicate cooler than average years, whereas the red bars show warmer than average years. It demonstrates that after 1900 the global surface temperature is increasing, and this increase accelerated in the last 50 years. The figure shows that the increase in CO2 density and the temperature increase are related. But what is the physical principle behind the relation between the CO2 concentrations and the global surface temperature increase? I will try to explain the physical principle using this simplified picture. Planet Earth is making orbits in space around the Sun. In principle, the planet Earth is making its orbits in a close to vacuum space around the Sun. This means that energy exchange between the system Earth and space is not based on thermal conductivity. But how does the total system of planet Earth exchange energy with space? The exchange of energy between Earth and space is based on electromagnetic radiation. First, the electromagnetic radiation from the Sun, which emits in the UV, visible and in infrared part of the spectrum, is incident on the atmosphere and surface of planet Earth. If not reflected, the solar energy can be absorbed by planet Earth. The incoming solar radiation has a heating effect. On the other hand, planet Earth emits electromagnetic radiation as well. However, planet Earth is doing this in the far infrared, as the surface of planet Earth is much cooler than that of the Sun. Through this electromagnetic radiative emission, energy and power is lost towards space, or in other words, the electromagnetic emission of planet Earth is simply a cooling effect. The energy balance of planet Earth is in equilibrium if the same amount of electromagnetic power is coming in as is going out. Heating and cooling of planet Earth is in balance. This is the case if the global temperature remains the same over time. However, since the Industrial Revolution, human activity has resulted in extra emissions of greenhouse gases like carbon dioxide. As discussed earlier, part of the extra emitted CO2 remains partly in the atmosphere. Carbon dioxide absorbed in the far infrared spectral range that partly overlaps the spectral range of the electromagnetic radiation that cools planet Earth. With other words, the extra CO2 in the atmosphere acts like a blanket and blocks a small fraction of the Earth's electromagnetic radiation into space in the far infrared. As a result, the power going out becomes smaller, the cooling is slightly reduced. How much is the difference? Dedicated measurements using satellites over the last decade show that on average a solar power per area of about 340 watts per square meters is incident, and electromagnetic power per area of about 340 watts per square meters is emitted into space. However, a subtle energy imbalance between incoming and outgoing radiation has been observed over the last 50 years, which is referred to as the positive radiative forcing expressed in power per area. From the period from 1971 to 2005, the radiative force has been on average plus 0.5 watts per square meters. In other words, 0.5 watts per square meters more radiation power is coming in than going out of the system Earth. In the period from 2006 until 2018, the energy imbalance increased to a radiative forcing of plus 0.79 watt per square meter. Although these numbers look very small in reference to the total incoming and outgoing radiations, these numbers are only 0.25% of the total radiance going in and out. It is still sufficient to cause the temperature increase of oceans and the surface temperatures as observed. You can do that with a simple back on the envelope calculations. Let's do that in the exercise following this video part 1. In the next video, we will explore different scenarios of rapid reduction of the CO2 emissions and how that will impact global warming. So, see you in the next video.